So the question that we had here was number 28, I believe it was.
Yes.
And we were supposed to show that cotangent has no horizontal tangent. So we have y equals cotangent of x, and then Jason found y prime to be negative cosecant squared x. And now he set this equal to 0 to find a hypothetical horizontal tangent. Maybe we could write it like this. At this point, this equation does not have any solutions, so we just say no solution, and we stop. That's it. We're not going to say that x equals 1 over 0 or any other such nonsense. If you find yourself saying equals 1 over 0, you know it's wrong, because this is not a value that can be equal to anything. Does that make sense? So the way in which we want to say that this equation has no solution is, it turns out, it's just the easy way, which is to say it has no solution. No, D and E is a different thing. No solution is different from D and E. D and E means does not exist, or is not a real number. So this would be a valid use of D and E. 1 over 0 does not exist. Is not a value. Right. Or the square root of -1 does not exist as a real number. Okay? Whereas no solution refers to an equation or inequality that does not have a solution.
So -1 over sine squared x cannot be equal to 0. That's why.
So there's no solution to the equation. Yeah. Does that make sense? Good. Okay, so it's just a language thing we needed to clean up. Now, yes.
I have one function for exclusive.
Okay, well, let me do a review, and then we're going to take homework questions, and then we're going to extend our work into more complicated examples of the chain rule. So our plan is review of the chain rule, homework questions, and then extend. So, yesterday we took a look at the derivative of compound functions f of g of x. And our derivative rule that covers this is called the chain rule. And we'll see why it's called the chain rule today with our examples. And what we found yesterday is that the derivative of f of g of x is f prime of g of x times g prime of x. Or as we like to call it, the derivative of the outside times the inside. Now, we had a proof of this. That proof, I think I want to go over a second time, just because it is helpful to us in terms of understanding the nature of the chain rule. And our proof begins with the left-hand side. We're going to get it to look like the right-hand side. And we start with our limit definition. We're going to evaluate f of g at x plus h. And we're going to evaluate f of g at x in order to get the difference between the y values. And we're going to divide by h to get the difference between the x values, and we let h go to 0. But now we pulled off a clever trick, which was multiplying by 1. I took all of this in the top, and I rewrote division by h as multiplying by 1 over h, and multiplied top and bottom quantity, g of x plus h minus g of x. And this is simply multiplying by 1 because these two factors really cancel each other. Now, the reason that we're motivated to do this is that this lets us now treat g as a variable. So I'm really looking at a difference quotient of f of g. I didn't need to rewrite that. Let's try that again. There we go. I'm looking at the difference in f on top over the difference in g on bottom. So this is really a rate of change with respect to g. And here I have the difference in g on top and the difference in x on bottom. So that's a rate of change of g with respect to x. Yes, this is a difference in x.
Oh, okay.
Yeah, exactly. That's right. Old school, we used to write h as delta x, and it was more clear. So now we pull off a little bit of product rule for limits. But we also pulled off a substitution. We said, since this is looking like a variable right here, let's go ahead and let w equal g of x plus h, and let's let w0 be g of x. And the reason for this is that by substituting, it's going to clarify that we're dealing with a variable on the side. So that now, when I replace g of x plus h with w, what I have is f of w. And when I replace g of x with w0, what I have is f of w0. And on the bottom, I have w minus w0 also, using the same substitutions from here. But finally, notice that h is no longer visible here, so I need to replace my limit. And I observe that as h goes to 0, w goes to w0. So that what I have on the right is straight up derivative, g prime of x. But what I have on the left is also straight up derivative. It is f prime evaluated at w0. And w0 is g of x. So that when I put this thing back where it came from, what I get is f prime of g of x times g prime of x. So that was our proof that we looked at yesterday. But also, we said that we could write this in Leibniz notation. So I could think of f prime of g of x as the rate at which f changes with respect to g times now the rate at which g changes with respect to x. And all of that is equal to, going all the way back here, the rate at which f changes with respect to x. So that what we end up with is something that looks like, although is not, but it looks like conversion factors. It looks like all I'm doing is canceling. But that's not really what's happening here. What's really happening here is that I'm multiplying two different rates of change that match in this way. The rate of change of the first is the rate of change of f with respect to g, and the rate of change of the second is the rate of change of g with respect to x, and their product converts this whole thing into a rate of change of f with respect to x. So we can think of it as very similar to conversion factors. In fact, conversion factors really are just constant rates of change applied to the chain. Okay. So that was our spiel from yesterday. Now, let's take a look at the homework questions you have. Number 15. Page 153. We can stall for time a little bit by simply saying that y prime is the derivative of what y is. I didn't do anything. I just announced my intention to do something. But by writing it like this, what it does is it helps me think, okay, now what derivative rule applies here? What product do you see? What times what? Does that sign mean times negative?
Is it minus?
It is minus.
I think it's
Of course it is. No, I would never write multiplication like that. Goodness no. That, if I wanted to write multiplication, then I would have to write it like this, so that there's no sign between them. When there's a sign between it like that, that's definitely subtraction. That's probably why there was difficulty here, just in terms of what is that thing. So, now that we understand that it's subtraction, we see that this is going to be the derivative of sine of minus 5x minus the derivative of cosine of 2x. Okay. And now what we've done is to break our complicated derivative into two simple parts, and we can take each one separately. So when I look at this guy on the left, I'm going to ignore what's happening over here. For the guy on the left here, what's my inside, what's my outside?
Sine. Negative.
Okay. Now we don't have a derivative rule for sine minus 5 to the minus 5. That's not a good choice for outside.
I think this is negative.
Ah, okay. So the outside is flat to the negative 5. What's the inside?
Sine.
Yep. Now you can keep on writing outside and inside as long as you need to so that it's helpful for you. Eventually you will get to the point where you can do it mentally. But I am going to insist, for now, until I give you permission otherwise, that when you actually execute the chain rule, that you're going to write the derivative of the outside like it is, and then write times ddx of the inside right there. I'm going to insist on that. Yes, you do. For at least a week. And the reason I say that is that when we get to our more complicated examples, doing it like that will give you a chance to think carefully and correctly without making mistakes. And then once you're good at it, I'll let you go. Okay? Jason? Next one. Good. So the derivative is?
3 cosine and d cosine.
There you go. Good. And the derivative of sine x is cosine x. And the derivative of cosine x is negative sine x. See the parenthesis right there? So we are indicating multiplication, and negative times a negative is a positive, so that when this all cleans up, we get minus 5 sine minus 6x cosine x plus 3 cosine squared x sine x. And this problem illustrates Kegel's informal law of conservation of grossness. Gross functions tend to have gross derivatives.
I think for 17 we have to do
Yeah, let's do 17. Y equals sine cubed x tan 4x.
Equals, parentheses, sine, sine x cubed, and x, I think, cubed, and that's tangent 4x times 4.
Times 4. I don't see times 4. What's happening here? I don't get what you're doing.
So that's inside, out, doing the chain rule. Well, I didn't do the derivative.
Do you have to use product rule?
Did you identify inside and outside? What inside function do you have here?
I forgot to write, or say the derivative, sine. So the outside is just parentheses cubed inside sine.
Okay, well, what about this? Isn't that part of your function?
Yeah, but you would do the product rule, or that's what I'm.
I mean, we are going to have to do the product rule.
But do we do that after or before?
Great question, and that's why I want to slow you down. So if you find yourself doing product rule and chain rule in the same step, probably time to slow down at this time. Eventually, you can fly through all those, at whatever pace you need to. But at this stage, we're going to do one derivative rule at a time. Now the question is which one? Do we want to do product rule first, or do we want to do chain rule first? And we can answer that by just saying, okay, let me try to identify either an outside and an inside, or let me try to identify two functions that are being multiplied. And sometimes it helps to just pronounce this out loud. So y is equal to,
Sine cubed x times tan.
did you hear yourself?
Yeah.
Times sine cubed x times tangent 4x. And that's the product. So, we're going to think in terms of first times the derivative of the second plus second times the derivative of the first. And Mark, this is a good illustration of why you definitely want to check your answers, right?
Well, I couldn't get through it all, so I couldn't check it.
Gotcha. Okay. So now what we've done is we've taken our complicated function and we've expressed it in terms, its derivative, in terms of two simpler derivatives. So I can now focus on just the derivative of tangent 4x without having to worry about anything else. So let's do that. When I focus on just the derivative of tan 4x,
Outside's tangent, and then inside is 4x.
good. So we get
Tangent, 4x times 4, the answer is 4 tangents.
okay.
13.
So take a look at the form again of the chain rule. ADX of f and g of x is f prime g of x times g prime of x, or as we sloganize it, the derivative of the outside times the derivative of the inside. Notice that it's the derivative of the outside, not the outside itself. So what is the derivative of that outside function tan? Nope, don't look. Derive it. If you don't know, you gotta derive it. Shh.
Sine over cosine.
Uh-huh.
That is sine. Oh, it's low b high and left side be low. So cosine, derivative of sine
Yeah, we can write that as cosine squared.
minus phi sine x over cosine squared.
Mhm.
It is cosine squared over cosine squared.
Hmm.
Separate,
Simplify apply that in the top first here.
Cosine squared x plus I sine squared x. Over first. And then, first.
There's something you're supposed to know about cosine squared x, cosine squared x. Does indeed. Which means, therefore, the way that the cool mathematician chooses to write it in this. Now, this is probably the second time you've done this?
I think it was the first time.
First time.
Somebody else did yesterday.
Got it. So, my recommendation to you is, do it for yourself at least 3 times, then you won't forget it. Do not rely on memorization if you can derive something, generally speaking. The only exception to that is if the derivation is like 3 pages. And generally speaking, derivation is much superior to just creating flash records. All right, so coming back to here, the derivative of tangent 4x, we've got outside is tangent slap, the inside is
Secant squared x. Right. Or secant squared 4x.
yep, secant squared 4x. We're going to write it as times the derivative of 4x. I know that you can do that derivative in your head, but you don't have permission to just yet, because, as we're going to see in just a little bit, by writing it like that, you give your brain some kind of space to think. Okay? Now, over here. Outside, inside?
Outside is parentheses cubed, inside is sine.
So the derivative of the outside?
Derivative outside is 3 parentheses cubed. Sine
Not cubed.
squared.
Squared.
And sine is inside. There's derivatives.
Don't worry about what that is next. Okay, good. That's here. This is our scrapboard. We can do this. And now we have sine cubed x times secant squared 4x. Now we have times 4. I'm going to write the 4 as the coefficient out here. If you wrote it over here, it would not be wrong, but all the cool mathematicians put their coefficients first. And likewise here, I've got a factor of 3 that I'm going to write as a coefficient here. So that I get tan of 4x times sine x squared times the derivative of sine x times sine x. Very, again, a kind of a gross derivative corresponding to our gross original function. Question? No question. Yes, question.
What is given 4x?
Here. This is the argument of the secant squared. It's secant squared 4x.
Oh,
Yes. When we take the derivative of the outside function, we do not touch that inside. Yes.
Where's the
Oh, over here?
that improve?
You have to prove the erasing.
Oh,
Yeah. You can do it for yourself.
the I have person.
Okay. Go ahead. Let's just walk through the whole thing. We'll start here.
Between cosine square x minus sine square x over
Should be plus.
plus
Let's go ahead.
Cosine is derivative of sine x.
Which is squared, yes?
And it's cosine squared x plus sine squared x.
Yep,
Or cosine squared x.
yep,
I know if cosine squared x plus sine squared x is 1.
yes.
If I divide by
Yeah. Hang on one second, and I'll finish that thought. That's secant squared x, right? But if I divide, and after all this is times 1 over cosine squared x, then I should get 1 plus sine squared x over cosine squared x, yes? But this is the same as tangent squared x. And one of our 3 Pythagorean identities is that secant squared x is the same as 1 plus tangent squared x. So it all works. Good question. Okay. Unless there are other questions, I would like to take a look at some more exotic examples. All right. Let's consider this. What is the derivative of the square root of 1 plus sine pi x? Now,
Square root of 1 plus sine pi x times cosine.
but remember that, at least for a little bit, we're going to write it as like this. And I know I'm slowing you down, but I have a reason for doing it. So what I've done here is outside inside, making you do the interchangeable. But now we take a look at what I have left. And what I have now, if you look closely, is another compound function. I have, what, 0 plus. But sine of pi x is really sine of something, and that something inside is pi x. So that we can now think of the derivative of 1 plus sine pi x as the derivative of the outside, that is 0 plus cosine of pi x, times the derivative of the inside of x. And this is actually why the chain rule is called the chain rule. What I really have here is a chain of 2 links. Outside, outside again, and finally we get down to a basic function whose derivative is just simply pi. So that when I put it all together, I get pi over 2 roots 1 plus sine pi x times cosine pi x. Yes.
Why? The derivative rule for root of square x is 1 over 2x.
The derivative rule for square root of x is 1 over 2x. Here? Well, think of this in terms of outside and inside. See it? So the major point here is the reason that I'm having you write literally the derivative of the inside there is that when you have a compound function that I need to apply the chain rule twice to now, then I can see clearly what the outside and inside function are for that function. Yes, without getting confused.
I think the procedure is wrong.
You think what?
Like you should put one over here. Like here. And here.
Okay, yep. I could do that. What I was doing was actually inconsistent. You're kind of right. Honestly, in my mind, what I was really doing was I'm saying my outside function is 1 plus sine. That's the way I was thinking about it mentally. But I think your approach to it is conceptually a little bit cleaner. So I agree with you. That'll work. It simplifies in exactly the same way.
Yeah. But if it's not like 0, but I don't.
Or if it's x
Right.
plus or
Yeah.
something like that. You're right. Yeah, that's right. Good. Very good. Okay. Let's take a look at a second kind of thing. Okay. So we have this kind of thing right here. Again, we identify outside and inside. What's the outside here? No. When this is written like this means that the entire thing,
Oh, sorry.
yeah. Left side. And so we take derivative of the outside times the derivative of the inside. Derivative of the outside is 2 sides flat times the derivative of the inside. And so the virtue of doing it in this manner, even though it's a little longer, is that it allows us to think clearly about outside and inside. Now I observe that this is also a compound function. Outside is square, and inside 2x plus 1. So I get cosine of all this times the derivative of the form, the outside, times the derivative of the inside. Whenever you look unhappy with something, check it. Got it. Derivative of 2x plus 1 is 2. And I'm going to collect the other factor of 2 that I had right there. And I'm done. Probably, honestly, the cool mathematicians would combine a little bit to write it like this. Does that make sense? Let's consider one that's actually in your homework tonight. Yes, ma'am.
Over here, sine 2x plus 1 to the square.
Uh-huh.
It doesn't, looks like the outside is this.
You're saying it looks like this?
Are we doing this?
I'm not sure what you're asking.
Because this should be equals to it.
Yes, this right here should be equal to this. Exactly. So this is not that. Yep. This is outside is sine, inside is. Yeah, you're okay. Yep. Okay, let's take a look at number 31. In number 31, we're given a function that looks kind of innocent. Y equals cotangent of 3x minus 1. And we're told to find y double prime. Okay. Get us started, Mark.
So first, we find y prime. The outside is cotangent, and the inside 3x minus 1.
Good.
Is the word 31?
Uh-huh. I don't remember exactly, but it's similar to.
And it's the derivative of cotangent, which I do not have any understanding.
Here we go.
Yeah, cotangent is this side. So it is low, so sine the derivative cosine of the single sine squared minus cosine times derivative sine cosine squared. It was negative sine squared x minus negative cosine squared x,
This would be what?
which is
Sine squared x plus cosine squared x is equal to 1. Yes.
but it's negative.
Indeed. So I would get negative 1. It would probably be written down.
Negative cosine.
But now just cosecant. Cosecant squared.
Yeah.
So, again, just want to emphasize the necessity of two things. One is to make sure that you know your six trig derivatives, because obviously this process takes a while. And second, the necessity of deriving them for yourself once a day for like 3 days until you have them. Okay. Now we're back. We have a derivative goal. And y prime is therefore equal to.
Negative cosecant squared 3x
Mm-hmm.
and then the derivative of 3x plus
Clean that up a little bit.
is 3. So it's 3 negative cosecant squared 3x.
Now, y double prime. Jennifer.
So, my double prime should be equals to negative 3 times the derivative of all of them.
Mm-hmm.
And there should be a product rule.
Okay. How's that gonna go?
F prime x times g f x plus g prime of x times f.
Okay. But in this case, make it concrete for us. What f and g are you talking about? In other words? What's that? Okay. So what options do you have? You mentioned product. If I'm going to think about cosecant squared 3x minus 1 as a product, what is it the product of? Oh, interesting. Yeah. When you do the derivative of the outside function, don't touch that inside. Okay. So don't stare at that too much. Take a look at what we have here. And let's rethink this.
The outside should be cosecant.
Like that? Okay. Do you have a derivative rule for cosecant squared? No.
Not cosecant squared, but cosine.
What's your outside function?
Let's just put the square like out.
Yeah. The square is the outside. Yeah. I agree. And the inside would then be what? Yeah. Here's the friendly pro tip. Your outside function always has to be a function that you have a derivative rule for. Has to be. Otherwise, you can't get anywhere with the chain. Okay. So now with that outside and inside identified, what is my derivative going to look like?
2
Now, no square.
No
Yeah,
square.
no square. Okay. Mhm.
times.
Yes, Jason's right. Jennifer, you're making it too hard because you're resisting simply writing here times the derivative of the inside. Outside, inside, simple. Not yet. We'll do that in the next step. You see what I mean? You give your brain a chance to think. Okay, let's see. Jason, you're next.
Negative.
What is the outside function?
Outside is cosecant
And the inside?
3x minus 1.
Okay.
My product for move for cosecant.
What is the derivative of cosecant?
Negative tangent, or
Should be cosine.
Now, it should be negative. The derivatives of all our cofunctions are negative. Negative.
cosecant.
Cosecant?
No, cosecant.
Cotangent.
Cotangent.
And cosecant of what? Good. And cotangent of 3x times the derivative of the inside. Because we're out of time, I'm just going to write it times 2. Come back and clean it up a little bit. Negative 3 times negative 6 is positive 18. We have a factor of cosecant and another factor of cosecant. And we have a factor of cotangent. 3x. Ooh, that was exciting. Yes.
Oh, so you multiply the cosecant together.
Yes, exactly. Uh-huh.
cotangent doesn't have a negative sign,
No, it's negative cosecant cotangent.
but don't we,
Well, it's -1 times cosecant times cotangent. Right, and you can order, multiply, and then you order equation. Yep,